Alright, in this video we're going to talk about Unit 3, Objective 4, use substitution. So up until this point, we've not really been able to take the antiderivative of anything but power rule and trig rules. More specifically, we haven't really been able to take the antiderivative of a composite function. So those are the functions that we would be using chain rule if we were taking the derivative. So if we're taking the derivative, we would be using chain rule, but we're going to be taking the antiderivative. So we're going to need to use the composite, or on a composite function, we're going to need to use something called use substitution. So to anti-differentiate composite functions, we need to use use substitution to antiderivative. So here's our rule. It's kind of a mess rule, but we'll kind of run through it real quick. The antiderivative of f of g of x times g prime of x dx equals the antiderivative of fu du, which is just going to be capital F of u plus c. So what this all means is if we have a composite function, some function inside of another function, g of x is inside f of x, we are going to rename g of x as u. We're going to replace g of x with u. So that's where this u comes from in fu. Dx, or I'm sorry, not just dx, but g prime of x dx is going to turn into du. So we need to notice that the derivative of what's inside, so the derivative of g of x, is part of the function. So our use substitution is only going to work if what's inside, if its derivative is also in the problem. So once we turn this thing into fu, we're just going to take the antiderivative like we normally would. That's where the capital F comes from. Then we're going to plug u into that. So that's going to be where our g of x is going to come back into play. So let's take a look, because this looks way more confusing than what's going on. The main thing that we need to make sure of is whatever's on the inside, its derivative has to be in the function, and we're going to call that inside thing u. So let's look at an example of what's going on here. We have the antiderivative of 2 times the square root of x or 2x minus 1 dx. So we know that we can rewrite that as 2 times parentheses 2x minus 1 to the 1/2 dx. And now we can kind of see that there's that inside function. If we had to take the derivative of this, we would be using chain rule because of what's in here. So if we look at it a little bit more closely, the inside function, 2x minus 1, we're going to call that u. Now in order for this to work, u prime, and let's actually not call it u prime, let's call it du, has to be in here. So if we take the derivative of u, that's du, right, derivative of u. The derivative of the right-hand side, so the derivative of 2x minus 1 is just going to be 2, and then we're going to say dx because we took the derivative of x. So it's kind of like an implicit differentiation, but you're going to kind of see why we do this. So the derivative of u is 2 dx, right? So the derivative of 2x, 2, and then we're going to stick that dx on there. The reason we're doing that is we have a 2 dx in our problem. So that 2 dx is going to be replaced by du, and 2x minus 1 is going to be replaced with u. So we're rewriting this problem to look like something we know how to take the antiderivative of. So we can replace the 2 dx with the du, and the 2x minus 1 to the 1/2 with a u. So u to the 1/2 du. Well, that's really easy to think about, right? That's just a power rule. So we're turning a chain rule into a power rule is basically what we're doing. So capital F of u is going to be, we're going to increase our power to 3/2, multiply by 2/3, and put c. But our answer, or our question rather, was in terms of x. Our answer right now is in terms of u. So we need to make that substitution one more time. We know that this u, oops, I meant to change the color there, sorry. We know that that u is 2x minus 1. So we can rewrite our answer as capital F of x is 2/3 2x minus 1 to the 3/2 plus c. And if you wanted to check, you can take your derivative, and we should end up at 2 times the quantity 2x minus 1 to the 1/2. So again, what we're looking for is the inside function. We're going to call that u. Take the derivative of u and see if we can find that inside our problem. So in this case, we had 2 dx, we have a 2 dx. So we're going to rewrite our function, inside function is u, turn our 2 dx into du, anti-differentiate like we normally would, and then plug u back into our problem. So let's try another example, because there's something a little bit different is going to happen here. So in this case, remember, whenever we have trig to a power, I want you to think of it as the trig inside some parentheses to a power. So inside our problem, we have our u, right? It's inside our parentheses, so our u is going to be equal to sine of 3x. So when we take the derivative of u is du, the derivative of sine of 3x is going to be u prime, so 3 cosine of u, so 3 cosine 3x, and then we put our dx. So there's a little bit of an issue here. In our problem, we have a cosine 3x dx, but du does not equal cosine 3x dx. du equals 3 cosine 3x dx. So we need to worry about that 3. But it's a really, really simple fix. All we have to do is divide. Right? If we divide each side by 3, we can get 1/3 du equals cosine of 3x dx. Now we have that substitution we can make. So 1/3 du is going to be equal to cosine 3x dx. So that's what we kind of have to, we can kind of be careful there when we check our du's. Sometimes we're going to have a constant that's not going to work out, so we're just going to divide it to the other side. That doesn't work if you have an extra variable, but the 1/3 is going to be okay, because what we're going to be able to do with that 1/3 is when we rewrite this, we can say u squared, and then cosine 3x dx we said is going to be 1/3 du, which we can rewrite as, we can rewrite as 1/3 u squared du, and since that 1/3 is a constant, we can pull that 1/3 out front. So we're going to be looking at 1/3 times f of u. F of u is just going to be increase the exponent to 3, divide by 3. So we're looking at 1/9 u to the 3rd plus c. Plug your u back in, so we're looking at 1/9 times sine of 3x to the 3rd plus c. And if you want, you can rewrite that as 1/9 sine to the 3rd of 3x plus c. So again, we want to find what's on the inside, call it u, take its derivative, try to find its derivative in the problem. We might have to adjust it, right? Move the 3 over to get just the derivative, cosine 3x dx, in the problem. And then anti-differentiate like we normally would. So it's going to change a little bit more when we go to take a definite integral. So if we're integrating from a to b, notice the other ones were just antiderivatives. We're going to have to change our limits of integration, right? Right now, a and b are x values, and that's okay because we have g of x, g prime of x, dx. Now this is u and du, so we need to change our limits of integration. So how we're going to do that is once we define our u to be whatever g of x is, our upper limit is just going to be whatever y value that was. So we're going to look at g of b for our upper limit and g of a for our lower limit. And then it's going to be the same process that we just took. So let's do that and then call it quits on this video. So we're looking at the integral from 0 to 1 of x times the quantity x squared plus 1 to the 3rd power. So let's start with our u. So our u is going to be the inside part. So our u is going to be x squared plus 1. Our du is going to be 2x dx. If we look in our problem, I only have an x dx. So I need to move that 2 to the other side. So 1/2 du equals x dx. So we know this piece here is 1/2 du. We know that piece there is u. So we can rewrite our problem as the integral. We'll worry about our limits here in a second. 1/2 u to the third du. Let's go ahead and pull that 1/2 out front. So 1/2 the integral u to the third du. Now we think about our limits of integration. So we need values of u. So u equals x squared plus 1. If we take 1, so we'll say either g of 1 equals u of 1 equals 2, right? Plug 1 in here, 1 squared is 1, 1 plus 1 is 2. 2 is our upper limit of integration. G of 0, if we're thinking about it as f of g of x, or just u of 0, right? Thinking about it that way, is just going to be 1. So now we have our upper limits of integration. Now, one thing I want to point out is if we look back at this, this is just f of u du, which means we're going to look at it as capital F of u evaluated from g of a to g of b, which means we do not go back to x values when we are integrating. Do not go back to your x values. This is just in terms of u. So take your antiderivative, use your fundamental theorem of calculus here. So to finish up the problem we were just looking at, capital Fu is going to be 1/4 u to the 4th power. And we're going to want to evaluate that from 1 to 2. So we're not going to go back to x squared plus 1 like we did on the antiderivative. Now, the one thing that you need to also be careful of is this 1/2 here, so we need to put that out front eventually as well. But let's just worry about this. Actually, we can put the 1/2 there. So this is going to be 1/2, excuse me, 1/2 of f of 2 minus f of 1. So if we put 2 in here, 2 to the 4th is 16, divided by 4 is 4. 1 to the 4th is 1 times 1/4 is 1/4. So 1/2 of that. So 4 minus 1/4 is 15/4. Times 1/2 is going to be 15/8. So the thing to remember on this one is we do not go back to our x values. We want to find our numeric answer in terms of u. So once we get here, we don't go back to x. It's just increase, divide, use your fundamental theorem of calculus. If you have a constant out front, make sure you multiply by that constant out front. So that's going to do it in this video. We'll see you in the next one.